What's the most useful household appliance that you have?
That's definitely the washing machine.
When did you buy it?
I bought it 2 years ago. Actually, my mom gave it to me as a birthday present.
Is it expensive?
I don't think it costs that much.
Hey everyone, welcome back to Understanding Motors. Last episode, we discussed how running current through a wire which is situated in a magnetic field can create a force on the wire, and then how, if we make a loop out of the wire, we can create a net torque on that loop. Let's start by exploring this idea a little bit more. As we said last time, the torque on this wire can be quantified as the cross product between the distances the forces are apart and the force vectors themselves, where the force vectors are the result of the current times the length crossed with a magnetic field. Now I know that all these cross products can make this a little bit less intuitive, so let's make some simplifying assumptions. If we assume that the magnetic field and the direction of current are perpendicular, as shown here, we can reduce this cross product of IL and B to simple multiplication, where the resulting force will, for the case shown here, point up and down. For the second cross product, we can use the fact that the magnitude of a cross product is equal to the vector magnitudes times the sine of the angle between them. Noting that our force vector will lead our current vector by 90 degrees, we can approximate our earlier equation of torque to be equal to DILB cosine theta. Looking back at the animation we showed last episode, we can now plot the torque on the loop as it swings through a revolution. From this, I want to point out two key ideas. Firstly, the torque is maximized when the coil is directly in line with the magnetic field. Another way to say this is that the torque is greatest when the magnetic field induced by the wire is perpendicular to the external magnetic field. I'll repeat that again because I know that it can be a tough idea to catch. The torque on the wire is maximized when the magnetic field induced by the loop of wire is perpendicular to the external magnetic field. This may seem like a silly thing to point out, but it'll be a very useful idea around episode 5. The second thing I want to draw your attention to is that because the torque on the loop goes down to 0 when the loop is perpendicular with the external field, this loop cannot be controlled to any arbitrary orientation. What I mean when I say this is that if this wire initially starts in the position as shown here, there's no current we can send to it which will move it out of this orientation. To fix this second issue, a motor uses multiple loops of wire, typically 3, each offset from the last by 120 degrees, and it switches the current path through these loops in a process called commutation. If these loops are 120 degrees apart, we could plot the torque that each would produce at any point during rotation. What we see is that at any time, running current across the loops in the direction indicated by the arrows always creates a positive torque in at least one of the 3 loops. So we can make it such that each one is active for the 180 degrees where they produce positive torque, then inactive for the remaining 180 degrees. However, if we did this, we aren't taking advantage of half of the times our loops are aligned with our magnetic fields. This would make our performance non-ideal, not to mention the headache of figuring out how to actually make this switching happen. Instead, what we will do is electrically wire our 3 loops together, such that when a current runs through one in a positive direction, as shown by the arrows, it will run through at least one of the other 2 loops in a negative direction. If we're clever about how we time this throughout rotation, this will allow us to flip the signs of these negative torque peaks, changing our 3 positive peaks into 6. But how do we electrically connect these loops to make this possible? Well, there are 2 ways, a Y configuration and a delta configuration. In each of these diagrams, the resistor squiggle denotes a loop of wire which would be aligned with the squiggle. It's worth noting here that the diagram doesn't necessarily match the geometric layout of the coils, but it's an equivalent electrical circuit. In both cases, we would have 3 wires, which I will call nodes, coming out of the circuit. If we connect one to a positive voltage and one to ground, we can now drive a current through our loops. In the case of a Y configuration, for example, a positive voltage on node A and ground on node B would produce current V over 2R in loop A and negative V over 2R in B, where V is the supply voltage and R is the resistance of a single loop. In the delta configuration, a positive voltage on node A and ground on B produces a current negative V over 2R in loops A and B and current V over R in loop C. Y and delta configurations each have their own benefits and shortcomings, and in practice involve slightly different motor constructions. However, they commutate in the same way. So going forward, I'm only going to show animations for the Y configuration, as I think it's a little bit easier to understand, and honestly, it's easier for me to animate. But I want you to know that the topics we're covering apply to both. If we were to look again at the torque curves for the 3 loops of wire revolving in a magnetic field and think about the case of the Y configuration, what exactly would we want? Well, at any time, we would want the loop which has the maximum positive torque connected to high voltage and the loop that has the largest torque in the negative direction connected to ground. In this way, the current will flow positively through the high positive torque loop and negatively through the negative torque loop, thus producing positive torque in each. If we play through the rotation of these coils, showing at each point which node needs to connect to ground as indicated by the black ball, and which needs to connect to high voltage as indicated by the red ball, we can notice a trend. The nodes only need to connect to the electrical circuit when they are within 60 degrees of parallel with the magnetic field. And to produce a counterclockwise torque with the wiring as shown here, it will always connect to ground on the left and power on the right. So we can actually achieve this torque configuration through some clever mechanical design. By having 2 brushes, one connected to power and one connected to ground, which only contact our loops when they are in these regions, we can have the turning of the motor take care of the switching of our electrical pathway. On a side note, in practice, the brushes are actually a small conductor which contacts a large conductive strip wired to each of the nodes. But I personally find that it's easier to conceptually understand brushed commutation depicted as a point on the node contacting a brushed surface. So now we know how to make our motor rotate from any arbitrary position. But where does this leave our torque function? If we actually wrote out our equation as a function of rotation angle, it's a 6-part piecewise function, where our output torque fluctuates about 14% periodically throughout rotation. This fluctuation is referred to as torque ripple, and we're going to talk about it a whole lot more starting around episode 8, but for right this second we're going to ignore it. If instead we calculate the average torque across a revolution, we find that our torque is proportional to the current running through the motor, the length of the motor, its diameter, and the magnetic field present. However, in reality, these aren't just 3 loops of wire. They're coils with many loops in each. Thus, we will add a variable, N, to this equation to represent the number of turns in each coil. Looking at this equation, we can separate our variables into 2 groups, those set by the user and those dictated by the manufacturer. That is to say that if you buy a motor, you don't have any control over the number of turns of wire, the length of the motor, its diameter, or the magnetic field strength of the magnets. What you do have control over is the current supplied to it. We will group all of these variables that are set by the manufacturer into one term, k-tau, the motor torque constant. This is a parameter which will be supplied by the motor manufacturers, and it says that the average torque produced in the motor across a single rotation will be the current times this one constant. Therefore, the torque our motor can produce is only limited by the current we can run through it. Now let's take a brief detour into the first law of thermodynamics, which says essentially energy is conserved. We can model a motor winding electrically like this: a resistor representing losses in the system to heat, an inductor which stops current from changing instantaneously, and a gyrator system which represents the conversion of electrical energy into a magnetic field and then into mechanical torque. The voltage across this last gyrator system is the back EMF. Accounting for Watt's law, which says that electrical power is equal to the current running through something times the voltage differential across this thing, we can say that the electrical power which is transformed into mechanical movement is equal to the current times the back EMF in the motor. On the mechanical side, we can state the power as the torque produced by the motor multiplied by the angular velocity of the rotor. Since energy losses to heat occur only in the resistive and frictional elements, not in the gyrator system, we can now set the electrical power into the gyrator equal to the mechanical power produced by the motor. Including our earlier equation for torque, we see therefore that the back EMF produced is equal to the motor's angular velocity multiplied by the torque constant. This means that if the velocity of the motor increases, the back EMF will go up proportionately. Because the back EMF is in the opposite direction of the supply voltage, as the motor turns faster, the net voltage across the resistive element drops, thus decreasing our current. What this means is that, as our motor turns faster and faster, the voltage we supply becomes less effective at driving a current, meaning that at a certain terminal velocity, which is equal to the supply voltage divided by the torque constant, we cannot make our motor turn any faster. So while our maximum torque is dictated by the current we can push through the motor, the maximum velocity we can accelerate our motor to is dictated by the voltage we can supply. So now we have some understanding of how we can make our motors turn, and we can quantify the limits of how we can turn them. Next episode, we're going to look at how to control the speed and direction of this rotation.